In this question, we're going to be figuring out the set of values in which this inequality is true. Now for this question, I would like to begin by simplifying this quotient here. The reason is because the same order of x is found in the numerator and denominator, which means I can simplify this further. And the way I'm going to do that is to rewrite the numerator as x plus 1, which is the same as what we have in the denominator, but then subtract 2 to make it equivalent to the expression above, and divide that by x plus 1, and this should actually give us 1 minus 2 over x plus 1. Now if I bring that back into the original expression, I will have the modulus of x plus 1, I'm going to put this in brackets for now, subtract 2 over x plus 1, and we're going to figure out the set of values in which this is less than 2. Now, this is quite a lot to deal with because we have an inequality and we have a fraction and we have a modulus operator. So what I would like to do is to actually just sketch the graph of y equals x plus 1 subtracted by 2 over x plus 1. So to begin sketching a graph like this, we're going to start with the simplest things we can think of, and that's asymptotes. And asymptotes, to get started, is I just need to figure out where this function isn't defined, and we can clearly see that x cannot equal minus 1, and that means there's going to be a vertical asymptote at x equals minus 1, so I'm just going to draw a dotted line over here. Now there is another asymptote, but it's not as obvious, and it's to do with this expression once again, this 2 over x plus 1. And if we think about what happens as x plus 1 gets very, very large, well, we can think in the limiting case of y that this fraction gets very small, such that it will basically be negligible. So we're going to approximate this to 0 and have y, the limit of y, just be dominated by this x plus 1 term. So that means we're going to have an asymptote that's not vertical or horizontal, but follows this equation x plus 1, which is just a straight line of y-intercept 1 and x-intercept of minus 1, and that's just going to be a dotted line through here. So now that we have our asymptotes out of the way, now we just have to figure out the shape of the curve, or at least how the function approaches each asymptote and where it cuts the x-axis and y-axis and things like that. So to figure out where it cuts the y-axis, that's easy. All we need to do is set x equal to 0 and figure out that y equals 1 minus 2 over 1, which is just minus 1. So we're going to have a minus 1 y-intercept. And an x-intercept, well, that's just going to be when y equals 0. So when y equals 0, we'll get 0 equals x plus 1 minus 2 over x plus 1. Multiply by x plus 1 on both sides, and we'll get 0 equals x plus 1 all squared minus 2. And this means that plus or minus root 2 equals x plus 1, and x equals minus 1 plus or minus square root 2. So this is going to be minus 1 plus root 2 and minus 1 minus root 2 here. So this is where the function is going to cut the axes. So in this case, well, we don't expect the curve to go above the asymptote at any point, and we can sort of intuit that with this expression here. As x plus 1 gets bigger, we're going to be subtracting less and less from the function, which means that it's going to be getting closer to the asymptote, but it's going to be getting closer in terms of getting closer by reaching it from below. So what that means is we just have to just connect these 2 points here, and there's probably a better way I can do that, and get close to this asymptote over here and reach this asymptote down here. And similar thing happening from the left hand side of the asymptote is by connecting these 2 points here, but just making sure it follows the asymptote there. Now this is what the graph will look like, and now all we have to do now is to add the modulus operator. So if we add in the modulus operator, so let's just say we're sketching y2, this would become x plus 1 minus 2 over x plus 1, And this is simple when you already have the function for without the modulus operator, because all we have to do is reflect any bit that's below the x-axis into the positive region. So this means this is going to be going up here. Good thing we worked out the y-intercept from below. And this bit's going to just go off like this. So this is going to be our modulus graph. And now, to relate back to the original question, we have to figure out when it's less than 2. So if we just sketch some value, some dotted line at y equals 2, we're going to see that it cuts the graph at 1, 2, 3, and 4 places. Now, because we know it cuts at 4 places, we need to figure out at the points at which the curve without the modulus function equals 2, the curve when the modulus function does equal 2, and we can then compare and contrast where our limits, where our inequality region lies. Find where the function equals 2. All we have to do is set y equals to 2 and then just solve for x. So this is what the equation would look like, and then multiply it through by x plus 1, and we will get 2x plus 1 equals x plus 1 squared minus 2. And then this would equal 2x plus 2 equals x squared plus 2x plus 1 minus 2. The 2x's go away, and we're going to be left with 3 equals x squared. So x equals plus minus s squared root 3. And remember, because our function had reflected parts where our modulus function, we had to reflect any parts of the original function below the x-axis in order to meet the modulus criteria. All we have to do to figure out where that function equals to is set our original function, the one without the modulus sign, to equal minus 2. This is the same as reflecting parts of the graph that are beneath the x-axis to the top, 2 over x plus 1, and then we do the same exact process, and we get minus 2 times x plus 1 equals x plus 1 all squared minus 2. Then we're left with x squared plus 2x plus 1 minus 2 minus 2x minus 2. So the minus 2's can go away, and then we're left with x squared plus 4x plus 1 equals 0. And for this, we'll just use the quadratic formula. X equals minus 4 plus minus square root of 16 minus 4ac, which is just 4 all over 2. And then we can simplify this to be square root of 16 over 2. And square root of 16 is actually root 3 times root 4, and root 4 is just 2. So we're going to end up with 2 square root 3 all over 2. And then if we divide through by 2, we will get minus 2 plus minus square root 3. So this is going to be, for the plus case, that would be minus 0.7, no sorry, 0.3, and for the minus case it will be minus 3.7, something like that. And we have all our values now, so we're just going to we'll just put that on the function. So this part is going to correspond to our solution here. It's going to correspond to our plus solution of square root 3. It's going to correspond to this solution, so this is going to be square root 3, and this is going to be minus root 3. It's not going to be clear, I'm just going to put that in brackets. And for our red graph, our red function, I mean, that's going to be minus 2 plus root 3 minus 2 plus root 3 and minus 2 minus root 3. Now all we have to do is figure out the range, this range here. I should give this a different color. This range here, it's multicolored for some reason, and this range here, And so that's actually going to correspond to uh, x being less than square root 3 and greater than minus 2 plus square root 3. And that's going to also be unionized with x being less than minus square root 3 but being greater than minus 2 minus root 3. And there our ranges of values for x satisfying this inequality above.